This is a problem about a grindstone. A grindstone is just a large stone that's a wheel, and you spin it, and then you use it to sharpen blades, sharpen a knife, sharpen an axe. And it's used because when you've got a large object to sharpen, you don't want to be sliding it along the stone like I do at home when I sharpen my knives and I'm sitting there with my whetstone just going again and again and again and again. You don't want to do that because you've got a much bigger job. So you get this stone up and spinning, and then you put the blade against the stone. Well, here we have this stone, and it is the coefficient of friction between, right, mu k, because it's moving. The coefficient of friction is 0.191. This is a great example of every week we're using everything in physics because you don't get to forget about the stuff we did before. All right, we know the mass of the stone is 73.9 kilos. We know the radius of the stone. I'm just going to go ahead and convert. 0.313 meters is the radius of the stone. Okay, so we know that we have a minimum that we want to be at, right, of 1.88 rotations per second. Okay, rotations per second. Well, a rotation all the way around once is 2 pi radians per rotation. So we're going to convert to radians per second because we need that for our equations. And if he gets a stone spinning up at 20.74 rotation per second, so he's up at this 20.74 rotations per second. Again, we're going to convert 2 pi radians per rotation. 2 pi radians per rotation. The blade on the stone, he applies it with a force, right? How long will the stone spin before it reaches the minimum and he has to stop and get it spinning again, right? So you get the stone spinning, you put the blade on it, you're sharpening the blade, working with the blade, and eventually you stop and you get the stone spinning again. Okay, so we know where we start. This is a mega naught. And this minimum that we're after is our final velocity, our final rotational velocity. So we're looking for the point where omega min equals alpha t plus omega naught. We know where we start. We know our minimum that we're going to stop at and start spinning the wheel again. But we don't know either alpha or t yet. In fact, t is what we're asking for. All right? So what's alpha? Well, you have to remember, right? Torque is I alpha. This is the equivalent of F equals ma. And so torque is I alpha. What is also torque? Torque is force times the distance that you've applied it through. Well, what force is being applied here to slow down the wheel? It's the force of friction. All right, so we've got the force of friction, and its kinetic friction is mu k times the normal force, and we're given the normal force, 1.63 newtons. So we know N is 1.63 newtons. We know mu k is 0.191. We've got the force of friction. So we know the frictional force, we know the radius. And because we know the frictional force and we know the radius, we know the torque. So torque is just Fk, all right, mu k N times R. We know the torque. All right. No torque. We know we have to use this formula. We go to the slide deck where we get the moment of inertia for a disk, which is what this wheel is. It's a solid disk, is 1/2 mr² And so we know the moment of inertia because we know the mass, we know the radius, we can figure out the moment of inertia. And so we can get to alpha, right? Alpha is going to be tau over I, torque over the moment of inertia. And all of that works out to, I'm running out of room, mu k n r over 1/2 mr squared. mr squared. So you can see it goes as 1 over r. I'm going to rewrite it over here. Alpha ends up being mu k n r over 1/2 mr squared. So we know alpha. We take that back to here. We know omega naught because that's where we start at. We know where we end up at, omega min. The only thing we don't know in this equation at this point is time. And so we solve this equation for the time, and once we have the time, we stick it in as the answer in Canvas. And that's how you get this problem done.